Welcome back to my channel, and in this video we are going to be talking about temperature sensors, that is translating heat into usable electronics quantity. Well, let's go on. Temperature is the world's most measured physical parameter. It indicates systems health. Let's go on. So how do temperature sensors work? Number one, they don't actually feel it like we feel it like as human beings. They don't feel it, but they react to it physically. And they do it in two ways. Number one, by resistance. The resistance changes as the amount of heat or the temperature increases or decreases. And the other method is by voltage. That is, the material itself generates its electrical signal, or there is a proportional change in voltage by increase or decrease in temperature. So there are four main dominant temperature sensors or temperature sensing technology. The first one is the thermocouples. So thermocouples they are rugged, and you find them in applications that requires rugged use. Then you have the RTDs. RTDs stands for resistance temperature detectors, and they are accurate. Then you have the NTC thermistors. These are common, the most common perhaps. NTC stands for negative temperature coefficients, and they are very sensitive to small changes in temperature. And you have the semiconductor-based temperature sensors. So let's explain what is a thermocouple. You ask, it works by using two dissimilar metals that are bonded together, and in some electric meters that has temperature sensors, you have thermocouples attached to them. They can be used to measure extreme heat. They can be used in measuring the melting point of metals and all, and they have a good accuracy. And then you have the RTDs, just like I said earlier, resistance temperature detectors. They are highly stable, but they are, however, very costly. We will not be doing that. You delve into this in this course. Then you have the NTC thermistors. These are the most common. They are highly sensitive, and they have fast response to changes in temperature. The NTC negative temperature coefficient means that their resistance drops as heat rises. The resistance drop as heat rises, and they can measure from minus 50 degrees Celsius to 250 degrees Celsius. So they are highly sensitive, which means that their temperature increases largely. The resistance increases largely per degree Celsius. And what are they used for? They are best used for fire detectors, battery safety detection, and current inrush protection. And the next one, you have the semiconductor-based one. They are actually integrated circuits in a board, or there are some ICs that they are also temperature sensors. So we can categorize that as semiconductor-based. And then there's another one. If you have ever seen an infrared thermometer, what they used during COVID era to measure the temperature on people's forehead, that's infrared sensors, and they don't need physical contact. All the sensors we mentioned earlier requires physical contact for them to operate, but an IR sensor does not require physical contact. They detect infrared radiation emitted by an object, but however, they are not accurate. And if you want more accuracy, you have to invest more into the sensor. So how do you choose which sensor do you want to use? As I said earlier, when you are looking at extreme heat, you can use thermocouples. When you are looking at medical precision, you are developing a product that you will need for medical use, you need RTDs, resistance temperature detectors. When you need fast protection, something that can react fastly, you use your thermistor. And in conclusion on this, just like I said earlier, if you need 1700 Celsius above, I don't know what you will use that for, but if you never can tell, you're going to need a thermocouple for that. For laboratory precision, RTDs is good. Thermistor is good for daily human use. And if you need to put it maybe on your board, you need an IC to do that. All right, having said that, let's do a little bit of practical. So here we are going to be using a temperature sensor to simulate how temperature sensors work. Unfortunately, in this simulator, there's only one temperature sensor there. They don't have a thermistor. They have this IC called TMP36. TMP36. So TMP36 is like a IC-based temperature sensor. It's all easy to use. So IC-based temperature sensor are actually very easy to use. There's another one called LM35, very easy to use. Let me help you a little bit. What is TMP36? You can come over here. Good. If you look at this, it tells me what it is for. Description: this sensor measures temperature. How it works: the device contains semiconductor material that changes electrical properties consistently with changing temperatures. The center pin's signal changes as the temperature changes, and the microcontroller's program can convert this signal from 0 to 1023 to degrees Celsius or Fahrenheit. From what I'm reading here, I think this sensor might be a digital sensor. Let's confirm that. We're going to browse online now. Okay, so the TMP36, according to this, is a low voltage precision centigrade analog temperature sensor. So we need to confirm that. And it gives a linear output of 10 millivolts per degree Celsius. So that means for every degree Celsius, the voltage at the output increases by 10 millivolts. You can measure between minus 40 degrees to plus 125 degrees. Okay, that's beautiful. Operating voltage 2.7 volts to 5.5 voltage, 5 volts. Scale factor 10 millivolts per degree Celsius. Output voltage is 0.1 volts, and like that. Okay, so that's beautiful. Let's go ahead to our simulator and continue simulation. So basically, we have seen from the simulation that from the data sheet that we read online that it requires 5 volts. So I need a 5-volt supply here. So we have this. Okay, we're going to use this power supply. Let's switch back to this power supply. Yes. So generate 5 volts. So I'm going to connect the positive to, this should be the power, you see that? This should be the ground. And I'm just basically going to connect this output to a meter so that you will see what we're talking about. The output goes to a meter. And the negative also goes to ground. Let's change the color. Black. Let's leave that. Red and black here. Okay, let's start the simulation to see. So 5 volts, that's beautiful. And the current draw is 50 microampere. So according to what the datasheet said, it says 10 millivolts per increase in temperature. So let me zoom in on this. I think that zone is too much. Okay, this is good. So this is 25 degrees. Let's reduce it. Let me see if I can. Okay, 39. That's 120. Let's see 38. 39, 110. 120, 38, 130. So that's equal to 10 millivolt change. 37 minus 37. Let's see. That's almost hard to get. All right, you see that, let me set it to 0 degree. At 0 degree, the voltage at the output is 500 millivolts. Ambient temperature is always around 25 degrees, and at that level, the output voltage is 759 millivolts. So as the voltage is increasing, you can use it to actually do something. So let's build something that's let's build a circuit, an analog circuit that turns on a fan when the temperature is high. So maybe you are building a stabilizer. You know, some inverters, yes, have this feature, or some stabilizer have this feature. The fan does not start running until it's maybe mildly hot. So we want our temperature at the point where it will start running to be, let's say, 40 degrees Celsius, 40 degrees, and that's around 900 millivolts, right? 900 millivolts. Okay, so that is noted. So this is what we're going to do. Delete this. We're going to take the input of this, the output of this, into a circuit that we can use to turn on or off our fan. All right, let's begin. For this circuit, I will need a resistor. Or there are circuits I've seen online before where they use a Zener diode as a barrier, such that until it crosses the voltage of the Zener diode, it will not turn on. Well, I will not recommend the Zener diode in this configuration anyway. The reason is this. Remember, when we measure the voltage of this sensor, the output voltage is fairly up to 1 degrees for that large change in temperature. And this Zener diode, most Zener diode voltage starts from 2 volts, 2 volts upward. So you won't find a Zener diode whose voltage is less than or more than, was less than 2 degrees. So what we can do, this is it. Now, let's first put in a transistor to see what we will get. Let's use an NPN transistor. So this is my transistor. Let's rotate it. I need resistors. Now the function of this, we want this thing to turn on when the temperature crosses 40 volts. So the temperature is increasing. Then when it crosses a particular threshold, it should turn on something. So let's see, let's put in a resistor. We'll first use it to turn on a LED before we bring in our fan. And let's start the simulation. Okay, let's make it bolder. So this is the sensor presently at 25 degrees, and you see the light is faintly on, right? The transistor needs at least 0.7 volts to turn on, or to start to turn on. Do you understand? And that is why this LED is faintly on. As we begin to increase the temperature, you can see the LED's brightness is also increasing gradually, and the voltage here is not really moving up as it should. Do you know why? I think that this sensor has been overloaded. What do I mean? The value of resistor here is 1K. That means it's probably demanding too much current from this sensor, so it is affecting the reading as it should. So the reading is not really behaving or moving as it should. It's just like putting too much load on your generator. You know how the voltage drops. Do you understand? So that's what's happening. So let's change this to 10K. So you see that, and then this is actually a 5 volt system, though. So the value of the LED should be 220 volts. Okay, that's beautiful. Let's change this further. You can make it, make it 47K. Okay, this is better now. You can see that even this is not the best kind of control because the voltage is so small. The changes in voltage is so small. The transistor here will be working in the linear range. Let me stop the simulation and remove this. Why? I'll change this load to like 1K and I'll connect this straight to the transistor. What we are doing now, we are exploring the use of transistor as an amplifier. So I'm going to connect another meter to the collector of the transistor. And then take this, connect the black wire to the ground. Don't forget to always do that. Is this 1K? 1 kilo ohms. And let's start the simulation. Okay, you see the output voltage of the transistor now is 4 volts. Let's go to drop the resistor until it gets to 5 volts. Let's going to increase the voltage. You see that it is dropping gradually, not at once, until 2.1 volts. It is dropping gradually. If it were to be a transistor as a switch, it's either when it's switching on, it switches on fully at once. And when it is switching off, it switches off fully at once. Then I think from here, you see I have 2.81 volts when it is, when the resistance, the temperature is fully on the highest. And then when the temperature is fully on the lowest, let's say like 16 degrees, the voltage at the output of the transistor is 4.75 volts. On the highest, it is 2.83 volts. On the lowest, so what we want to achieve is that when the temperature crosses 40 degrees Celsius, it should turn on a fan. So this is 4.42 volts at 40 degrees Celsius. So as we increase the temperature, the voltage at the output reduces, and as we reduce the temperature, the voltage increases. We are going to make use of these characteristics to adjust the speed of a fan. Do you get that? To adjust the speed of a fan. So what we're going to do now is that let's stop the simulation and we're going to attach this to the base, the output from here to the base of another transistor. Okay, having done that, we're going to I set this to 47K. Let's see how it responds, whether it is doing what we want to do. Okay, so presently, when the temperature is low, you can see the fan turning slowly at 123 rotations per minute RPM. If we begin to increase the temperature, it's now on 39. Let's see what RPM we have. 65, and it's almost zero with high temperature. That's not what we want, right? We want the temperature we want the speed of the fan to increase as temperature increases. So what we're going to do is we're going to use an inverter circuit to first invert the uh, the voltage before we pass it into this amplifier here. So let's stop simulation. I'm going to move all of this. I'm going to shift it a little bit to the right. I will delete this. I still need this. So I need my NPN transistor again. And my NPN transistor. So you know the circuit you want to draw now. An inverting circuit that inverts whatever comes into it. So the positive goes to positive. Negative goes to ground. And the base is connected to this junction. Let's change the color to green. So you have this. Oh, of course, there should be a resistor in between here. I'm going to have to delete this. I'll put the resistor. Let me just copy this and put it there. I'll change the color to red. And there you go. So I'm going to now connect the base of this. Let's make it green. I'm going to connect the base of this now to this. Okay, we've done that. Let's see how this works now. So the temperature is minus 25. As I increase it, did anything happen? Nothing happened. Let's see what we are doing wrong. I'm going to bring in another meter. Let's bring in one more meter. And this time the meter will measure the voltage at this junction. The negative goes to the negative. And let's see. So at this junction I have 67 millivolts. No matter what, so it's not actually turning on. It's not turning on. Okay, let's see what could be the cause of that. I will drop the resistance of this to 10K. Okay, it's still not turning on. Okay, could it be because there's no resistor here? Let me put a resistor there. Okay, let's see. It's definitely not because of the resistor. Um, good, good. So what we did was that we increased the value of this resistance to allow the transistor to completely switch off and completely switch and not completely switch on when the so we maximize a section of the thermistor so that a temperature section. So what we are interested in is between 25 degrees to maybe 40 thereabouts. So at that temperature range, we have enough that can turn on this fan, and you can see at 13, 21, 30. At 30, the fan has started working. So the fan turns on at 30 degrees Celsius to start cooling the system. So this is a very simple temperature controlled fan that you can deploy in your applications to make it smart. Thank you very much.